All right, guys, grab your notes. We are going to look at biomolecule number 2, lipids. So this is literally directly behind carbs in your note packet, another big table. Should be pretty quick. All right, so lipids. First thing we need to know, out of our 6 elements of life, what atoms out of those 6 elements of life actually make up lipids? So we have carbon. We have everything's made of carbon again, just like carbs. Hydrogen, and oxygen. But in your brain you should be thinking, oh no, this is literally exactly like carbs. How the heck am I going to tell the difference between a carb and a lipid if I'm looking at them? I'm going to give you a little hint. So remember, carbs were found in ring shapes like pentagons or hexagons and in a 1 to 2 to 1 ratio. Lipids are not going to be like that. We find lipids in very long chains, so long lipids. And the 1 to 2 to 1 ratio is not a thing here. So we're going to have lots of carbon, so I'd put maybe a little star next to carbon, and lots of hydrogen, and just a little bit of oxygen when it comes to lipids, but lots of carbon and lots of hydrogen in very, very, very long chains. Other names, so we don't normally use the word lipids, but you definitely have used these words before. So lipids are fats, oils, waxes, steroids, and cholesterol. So generally, you're probably most familiar with like fats and oils, like animal fat. That's how what we store on our body. Oils we cook with. Waxes like earwax. Steroids we often think of like bodybuilding. When people are doping, they take steroids. And cholesterol is a type of steroid, but really important for function. So it's not a bad thing, even though we generally associate cholesterol with bad things. So these are the other names. So take a quick second, highlight your elements, your carbon, hydrogen, and oxygen, and the fact that they're in long chains. So you should have your highlighter out, highlight that. So remember, we are building polymers, larger structures, so we need to know the monomer. What the heck are we using to build this larger structure that we're going to call lipids? So you're going to have some different ones here. So you have something called a glycerol molecule as a building block of fats, and then fatty acid chains. So fats are lipids, so we should be able to easily remember fatty acid chains. And again, they're really long chains made of carbon and hydrogen. So you're going to write down both of these things and you're going to highlight them. And then we're going to talk a little bit more about fatty acids, but take a minute, write it down. So fatty acids can either be what we call saturated or unsaturated. So if we take a minute and think about the word saturated, if the ground is saturated with water, or a sponge is saturated with water, it means it can't hold anymore. It's literally like the water cannot go in anymore into that thing. So saturated fatty acids are saturated with hydrogens, all right? So they have as many hydrogens as it possibly can hold. But how you can recognize it is between all of the carbon atoms, we have single bonds. And remember, covalent bonds are always depicted as solid lines. So between all of these carbons, we only have single bonds. This is an example of a double bond right here. It doesn't count because it's between oxygen and carbon. So all single bonds between your carbons and all these hydrogens. So every carbon has the maximum number of hydrogens that it can hold. So saturated form straight chains with single bonds. And they're solid at room temperature. So this is things like butter. Butter is a saturated fat. So at room temperature, it might be soft, but it is solid. So if we have saturated, we also have unsaturated. So we have in these chains at least one carbon to carbon double bond, so between 2 carbons. And what that is going to do is it's going to bend the chain. So it's not going to be nice and straight like this. It's going to actually curve because double bonds have a different angle that they need to kind of hold to be stable. So unsaturated, we go along, you have this double bond right here. And because there's a double bond here, each of these carbons only has 1 hydrogen, where up here, each carbon at least has 2. So that's why I mean it's unsaturated, it's not full. And these are going to be liquid at room temperature, so this is going to be like oil. Because what's going to happen is when at room temperature, they can't pack really closely together because of this bending. So the fact that the molecule's bent kind of puts distance between itself and the other molecules inside of the oil. These guys can pack really closely together because they're all straight, so they're not taking up much more space. So polymers, this is what we're building, the larger structures. So what can we build? The first one is a triglyceride. Tri, like tricycle, means 3. So it's 3 fatty acids joined to 1 glycerol molecule. And this is what it looks like. You have this picture. It looks like there's a line above the picture in your notes. That's not a thing. It's just the border of the picture when it got put in. So you can ignore that. You don't need to write anything. That's not a real line. But you might want to actually go ahead and label. So this right here, on my screen it is blue. On yours it's kind of just a lighter color. This is your glycerol molecule with the 3 carbons and the hydrogens. So you might want to label that glycerol. And then each of these, 1, 2, 3, those are your fatty acids. 2 of them are saturated, 1 of them is unsaturated. So you might want to just know the difference between them. So if you need to, pause it right now and label your molecule. Please remember to join these fatty acids to the glycerol to get this bond to occur right here. We needed to do dehydration synthesis. So we removed water. So 1 water got removed here, 1 water got removed here, and 1 here in order to join each of these fatty acid tails to the glycerol molecule, dehydration synthesis. So triglycerides are a very common polymer. And there you go, they're labeled for you. All right, this one is really, really, really important. That's why it has like 4 stars right next to it right now. Phospholipids. Phospholipids build cell membranes, and we're made of cells, so we need these guys. They're really important to keeping us healthy, to keeping our cells healthy. And what it is, it's 2 fatty acids joined to a glycerol. So not 3 like a triglyceride, just 2. And this is incredibly important. After you write it, I want you to highlight it. Only these lipids contain phosphorus in addition to carbon, hydrogen, and oxygen. So every other lipid is only going to be CHO. Phospholipids, that's what the phospho means, phosphorus, have CHOP. They are CHOP. And it helps with their function, which we're going to talk about. So highlight that. They make up the plasma membrane of all cells. The fatty acid tails are nonpolar. Remember, carbon and hydrogen, they share their electrons evenly and equally, so there is no polarity, there is no charge, and they are hydrophobic. They don't get along with water because they're neutral. So hydrophobic means water fearing, so water phobic or phobia is a fear. So they are called nonpolar or water fearing, hydrophobic. However, the phosphates, it's at the top of the phospholipid, it's polar, so it has a charge. And it's hydrophilic, meaning it's water loving. It can get along with water because it has a charge, so they can actually interact with each other, unlike the fatty acid tails. So here is a picture of a cell membrane. So the cell membrane goes around the entire outside. So this is, imagine if you cut the cell in half and you could see the inside. This is the entire outside. And if you zoomed in, each of these little guys with the purple heads and the 2 little squiggly tails, those are phospholipids. And it's 2 layers. So you have 1 layer with the heads facing this way, 1 layer with the heads facing this way. It's because you're made of water. So outside the cell, you have tons of water, and inside the cell, you have tons of water. So the heads are going to point toward the water. The tails are going to point, because they're nonpolar and hydrophobic, they're going to point internally in this kind of little safe space right here where you're not going to find a lot of water. And you have this picture on your note sheets. This is a phospholipid. The only thing on your note sheet that's not really great, that you can't really see, this part right here didn't copy well. So you might just want to put like a circle around that part on your notes, because the circle does not really show up on your notes. But you have your phospholipid right underneath with the polar head and the nonpolar tails. So that's what it looks like. It looks like a little jellyfish. And then the last one are waxes. So examples, earwax. So you all make earwax. And the reason is your ear canal goes into your eardrum. You don't want bacteria to get in there. That's how you get ear infections. So the wax is actually going to help trap the bacteria and not allow it to get into the eardrum. Most of the time when you actually get infections in your ear, it's because you had a sinus infection. So the sinuses in your face kind of circle around. They're all hollow. And if they fill up with mucus and bacteria, that can actually get to your ears and cause an infection behind the eardrum, which you don't want. It's very painful. So earwax is going to help with that. So here's a picture of an ear. Here's the eardrum. This area behind can fill up with fluid, not so fun. And here's earwax. So again, trapping of bacteria. If you think about leaves or fruits, generally, a lot of them will have a waxy kind of coating, and that's going to help prevent water loss, so the plant doesn't actively lose water all the time. Because remember, unlike you or I, plants cannot go in search of water, so they need to be able to conserve it. So having a wax coating around the outside is going to help keep that water in, because the water can't move past the wax. So here's a waxy coating on a leaf. You can see it's kind of shiny, and that's why generally the water is going to bead up right here on the leaf, or wax on apples. So it's kind of shiny. That's why they're shiny, because they're covered in wax. All right, so polarity solubility, you guys should know this. No, lipids do not dissolve in water. They are non-polar. They do not have a charge. It's like oil and water, right? They cannot mix. They don't get along. So lipids are not soluble in water. Very important. So they are non-polar. They are hydrophobic. So oil and water don't get along, don't like each other. All right, functions in organisms, you guys, after you write this, are going to highlight it. First one, long-term energy storage in animals. Some of us may not like this, but we store our long-term energy as fat. So if we take in more calories than we burn, our bodies are really good at holding on to it. Because evolutionarily, there might have been times where we had a lot of food and then times where we had less food. So those of us who could store our extra energy that we take in and didn't use had a survival advantage. So when you store fats, your body's saying, hey, there might be a time where I don't have access to food, and this is going to be a way that I will still be able to get all of these trillions of cells in my body the energy that they need. Which is why you lose fats if you start exercising or if you cut your calories, because you're spending more energy than you're taking in. So long-term energy, long-term lipids. So here's just fat cells. They're little storage cells. So you don't actually get more fat cells. You just kind of stuff more things inside of them. Insulation. If I live where it's very cold, fat actually adds a good layer of insulation, keeps all of my internal organs nice and warm. So things like polar bears or just bears, seals, anything that's going to live in cold environments or hibernate for a very long time, it's going to need a lot of insulation. And then really importantly, put a star next to this one, making up plasma membranes of cells. Those are our very special phospholipids. So our special lipids that have a little bit of extra than regular lipids. And again, here's just a little picture. And the phospholipids look like little jellyfish. There's tons of other stuff in the membrane. We're going to talk about that. All you're worried about right now are those little phospholipids. Then before I move on to proteins, I'm just going to go back. I don't think it's going to come up on the screen. Food examples: butter, oil, steak. Steak has lots of fats. I think butters and oils are your good ones that you can write down. I'm not super concerned about the food examples. So before you move on to anything else, or before you close this out, make sure you have your elements highlighted, your monomers, so your glycerol and fatty acids. Make sure you have under phospholipids, where it's starred, only these contain phosphorus along with CHO, and then the functions in organisms. Make sure all that's highlighted before you close this out.